We're going to take a look at VSEPR shapes today. VSEPR stands for valence shell electron pair repulsion, which is a really long name that you don't need to remember. All pairs, what you do need to know, is that all pairs of electrons, either bonding or lone, repel each other in a molecule, and want to move as far apart as possible within that molecule. So bonding pairs are organized and don't repel as much as lone pairs do. They create a large cloud. So we'll get to that. What we need to know is how to determine the VSEPR shape. So draw a Lewis dot diagram. We need this. It is a non-negotiable. You must start with a Lewis dot diagram. We need to draw all lone and bonding pairs specifically on the central atom. Those are the important ones. So there might be multiple central atoms. We need to make sure that we've drawn an accurate Lewis dot diagram. We're going to count the number of bonded atoms, so how many things are connected to our central atom, and the number of lone pairs on the central atom. So how many bonded atoms there are, it doesn't matter how they're connected. So if we have something like this, there are 3 atoms bonded around the central atom here. We have a hydrogen, and then this double bond counts as 1 bonded atom. So we don't double count here. There are still just 3 bonded atoms, okay? Same if we had, let's say, a triple bond. In this case, there are 2 bonded atoms. This triple bond acts as 1. So we're going to use a general formula to represent how many things are around this. So our general formula is AX something, where we'll have a number, E something. Where A is the central atom, so its number doesn't ever change. It's always a 1 here. X is the number of bonded atoms, and E is the number of lone pairs on our central atom. So let's look at our first example here. Let's write the general formula. So the central atom is carbon. The number of bonded atoms to that central atom is 3. And there are no lone pairs on our central atom. There would be lone pairs on this oxygen here, but they don't count. They're not on our carbon atom. So E is 0, so we don't have to write it. Over here, we would have had AX 2 because there are 2 bonded atoms, and no lone pairs on carbon means there's no E. If I have something like this, let's write the general formula here. AX, there are how many bonded atoms to our central atom of nitrogen? 1, 2, 3. And there's 1 lone pair here on the central atom, so we have E. We don't have to write E1, it's like writing 1x. If there's multiple, you do need to write that number. So when I write this, each of these corresponds to a VSEPR shape name. So let's get started on them. So the number of bonded atoms, the simplest we can do is 2 things bonded to a central atom. Something with only 1 atom bonded like this isn't actually, it doesn't have a central atom. The only distance apart these 2 things can be is 180 degrees. Okay, so if we have 2 bonded atoms, suddenly we can have some shape. So we represent our central atom with an A. And then we will write our external atoms, or our bonded atoms, as an X. See how this follows our general formula of AX some number, E some number? All right, now remember these are organized. So how far apart can 2 things be? Well, the furthest apart that these bonding electrons, remember, a bond has 2 electrons in it, each one. Electrons are all negative. They don't want to be next to one another then, so these bonds kind of repel one another. The furthest apart they can get is 180 degrees. So some examples of this are CO2 and HCN. So if you want to draw them, you can. When I draw a real molecule using a VSEPR shape, I actually include the atoms bonded. I don't draw my general VSEPR, okay, with the A's and X's. So CO2 here, there's no lone pairs on carbon, and it has 2 bonded atoms. So it's AX2, and again, they are 180 degrees apart. HCN, I'd drawn just a little bit earlier. We have HC with a triple bond to an N. Again, this is AX2, no lone pairs on our central atom of carbon. The furthest apart these 2 bonded atoms can get is 180 degrees. So although we know that it's the electrons repelling, when we were able to measure these in the lab, we're able to measure how far apart this atom is from this atom. We're not able to measure how far apart the electrons are. We're just assuming that they would, of course, follow that bonded atom that they are with. Okay, next up would be 3 bonded atoms and no lone pairs. So this one is called trigonal planar, and it would be AX3. So we draw our central atom as an A, and the furthest apart that 3 things can get in 3D space looks like a peace sign. So these are 120 degrees apart. Again, it looks like I'm measuring to the electrons, but remember, it's the atoms that we've measured between. We assume that the electrons are the reason that they are repelling one another and getting as far apart as possible to 120 degrees. Some examples are CO3 2-, so the carbonate ion, and I'm going to draw a boron here. So boron, technically, like if we were to go through our Lewis dot diagrams here, boron has 3 electrons, and each hydrogen has 1. So we only have 6 electrons to distribute within our molecule. So when I draw it like this. Boron's in the middle, hydrogen's all around. I've drawn 3 bonds. I'm out of electrons. So I asked myself, is everybody happy? Well, hydrogen only wants 1 bond, so it's good. But boron only has 6 valence electrons right now. It does not have an octet. What we need to know is that there's actually no way to make an octet. There's not enough electrons. Boron is an exception to the octet rule. Boron only wants 6 electrons. And that's just because of boron's size. Maybe it doesn't have enough room to have 8 electrons comfortably around it. But anytime boron is our central atom, it's happy enough to just make 3 bonds. Okay, let's continue on with our VSEPR. Reacquaint ourselves here. So the last diagram we had was 3 bonded atoms. So what happens if one of these bonded atoms turns into a lone pair? So what we'll draw is we will draw A with 2 X's and a lone pair. Now, initially, I said that lone pairs take up or repel more than a bonded pair. So what that means is a lone pair takes up lots of room. They're not quite as organized as the 2 electrons that are within a bond. These have a nice specific spot they need to be in. They're in line here. These 2 electrons are just kind of running around willy-nilly. So what I do is I remind myself of that by drawing them in a cloud. I remember that a lone pair takes up more space because I draw a cloud around it. So in your VSEPR drawing, you are free to draw that. All right, now if this takes up more space and repels more, then this angle was originally 120 here. Each one of these angles is 120. So this was originally 120 with just a regular paired bond here. Now I've taken up more space by these 2 electrons, so I've pushed these 2 closer together. Therefore, their angle now will simply be less than 120 degrees. They get a little bit closer together because that lone pair takes up some extra space. Some examples, the nitrite ion, SO2 and O3. So let's draw SO2 here. SO2 ends up with a double bond and some lone pairs on these guys. So sulfur has 2 bonded atoms and 1 lone pair. Therefore, the angle between these 2 oxygens is less than 120 degrees. So once we get to the point of more than 3 things, whether those things are 3 bonded atoms or 2 bonded atoms and a lone pair, once we get to this point, once we start adding one more thing to get 4 things around our central atom, whether that's 4 bonded atoms or a combination of them with lone pairs, we have to start considering 3 dimensions. So in the plane of the page is what we have been drawing right now. So our central atom is connected to some sort of atom, and if we were looking at it, it would be flat in our hand. Now, we'll also have atoms that come out of the page towards us. Okay, when that happens, we draw the bond as what we call a wedge. And last but not least, we can have atoms that go into the page. And so we draw these as what we call a dash. Some drawings actually include them as like dots. I prefer to draw mine with these lines just because dots can sometimes be confusing when we have a Lewis dot diagram. All right, so the order of repulsion is talking about electrons. Again, remember VSEPR is based on electron repulsions. So who repels one another the least? Well, this would be a bonding pair to a bonding pair. So for instance, in our AX3, these guys repel each other the least. Who takes up the most? Well, remember, lone pairs repel more. So more repulsion would come from a bonding pair to a lone pair. What this means is this takes up more space. They push harder against one another. So if this X became a lone pair, this repulsion between these 2 pairs of electrons increases. Now, the greatest amount of repulsion is if we have a lone pair to a lone pair. So if we have a molecule where, I guess I'll go back to this one just to keep it simple. I have 2 lone pairs on my atom. These 2 lone pairs are going to push one another super far apart. This is much stronger than the repulsion between a lone pair and a bonding pair, which is greater than the repulsion between just simply bonding pairs. This one's like okay. Again, this affects our bonding angles. So this is how we get our bonding angles. All right, last one here is when we have 4 things around our central atom. So if we have 4 things around our central atom and all of them are bonded atoms, we get something called AX4, which is a tetrahedral. So typically we would draw something like, let's say carbon with 4 H's. Our Lewis dot diagram looks like this. This would lead us to believe that our bonding pairs here, our hydrogens, are 90 degrees apart. However, this is assuming it's flat, okay? That they cannot pop out into 3-dimensional space. But we know that in real life, they can. So what happens is we have our central atom, and what we're going to do is we're basically going to start with our AX3 shape, okay? So we're going to put X and X. But I need to fit 4 things here. So I'm going to draw a wedge out and a dash behind on one of those arms. At the end of it, the wedge and the dash, I'm going to include my bonded atom. Now, this is really hard to see and understand the way that we've drawn it. So please make sure you take a look at the PhET simulation or some online kind of thing to understand what this shape looks like in real life. All right, so now that they've accessed three-dimensional space, they have a little bit more room than the 90 degrees, okay? It's a larger space for them to occupy. Between all of these atoms is 109.5 degrees. So between these two, it's still the same. Between these two, it's like a pyramid is what this looks like. So if we had a triangular-based pyramid, our central atom would be in the middle here, very center of this pyramid, and all of our bonded atoms are on the outside. That's kind of the way we can describe it. That's how it got its name tetrahedral. If you counted the number of faces on a triangular-based pyramid, you have 4 sides. Some examples, CH4, which we drew as a Lewis dot diagram, but if I were to draw it as a tetrahedral, I get something like this. So our ins and out of the page, when we draw them, they typically go right next to one another. Okay, what happens if I take off one of these bonded atoms and I replace it with a lone pair and I get AX3E? This is called trigonal pyramidal. So we're going to start with our A, and what we've done is we've replaced the top bonded atom with a lone pair. So our X's are all the same as our tetrahedral. We just draw them as the same. Now, a lone pair, remember this one is repelling even more than our original bonding atom here. Therefore, these angles used to be 109.5, and now they need to get a little bit smaller because they're being pushed further away from this lone pair. So our bonding angles in this case, it's not just less than 109.5, unfortunately, it's 107.3. Some examples, NH3 and PCl3. I could draw NH3 here for you. And again, we get something like this. Our last one. We replace one more of these bonding pairs with a lone pair. So I'm going to get 2 lone pairs. Remember, these repel the most. They want to get further apart. And I have 2 bonded atoms, and I can draw them in the page as usual. This repulsion also increases. Therefore, if we've started at 107.3 and added another lone pair here, the repulsion increased. It gets less than 107.3. And again, we can measure this one, and it is 104.5. I call these the radio station angles. That's kind of how I remember them. I got 109.5, 107.3, and 104.5. I just feel like a radio announcer when I am talking about those angles. An example is water. So water has 2 lone pairs and 2 bonded atoms. The angle here is 104.5, and that's actually where they measured it, is using water. Okay, so some homework for you guys. Double back to that worksheet, the Lewis Structures worksheet, and you can fill in all of the information for the general shape, the VSEPR name, and the angles. You can also draw the stereochemical or 3D shape. Stereochemical just means your VSEPR drawing. And use PhET. There is a simulation link on our website to help you with this. All right, it'll help you to understand what this looks like in 3 dimensions because we don't have access to bonding kits right now or molecular model kits.